Hi everybody, welcome to the next lecture on Multimediale Werkzeuge, this time on quantization. So this is the next step for compression. So for each 8x8 block we get 64 subbands in different spatial frequencies. So horizontally 8 and vertically 8 subbands from the DCT. So as we have seen, the different spatial frequencies have different visual characteristics. For instance, DC, the subband 0,0, contains the smooth areas, whereas the higher subbands contain correspondingly finer details. The goal here is a representation of the subbands with as few bits as possible. Fewer bits means coarser representation of the subbands, and coarser quantization with larger step size, or quantization steps, means larger quantization errors. The problem is these quantization errors occur in the reconstructed image. So we want to avoid seeing them. The approach is to select and distribute the quantization error for the subbands such that the error in the reconstructed image is as inconspicuous as possible. So best case, we don't even notice. Decomposition into subbands is useful because the subbands already have concrete visual characteristics. For instance, DC is the average brightness in a block, then the higher subbands have increasingly fine details of the image. We will use different quantization step sizes and hence number of bits for each subband, and that's accordingly to the sensitivity curve of the eye, the contrast sensitivity function, for different spatial frequencies. So the spatial frequencies at which the eye is more sensitive, the quantization is chosen finer, which means we have smaller quantization step sizes, which need more bits. The other way around, spatial frequencies at which the eye is less sensitive, coarser quantization with larger step sizes is possible with fewer bits, right? So this then saves bits, and this is mostly at the higher spatial frequencies where the eye is less sensitive. Yeah, so here in a remark, the quantization refers to the brightness values or amplitudes of the subband images. For comparison, the original usually has 8 bits per pixel for the luminance or the primary color components. The quantization step sizes can be represented in a matrix like the following. So, like this. So here we have our DCT output. Up here is DC. So here we have the lowest spatial frequencies. So here you can still see German language descriptions. So this means lowest frequencies. Here we have 8x8 subbands. And for each of those subbands we have defined a step size for the quantization. So this is the quantization step size. And at DC, JPEG, for instance, for one of its quantization matrices uses 10 for DC and 156 for the highest spatial frequencies, vertical and horizontally. And this is because the eye is most sensitive for this low frequency region where we have a relatively small step size of 10, or quantization step size, and for the highest frequencies the eye is least sensitive, and that's why we can afford to have the highest step size, meaning the coarsest quantization and the fewest bits. Yeah, so the eye is, if the eye is more sensitive, then we have finer quantization, which is the case here for the lowest frequencies. And where the eye is less sensitive, we have coarse quantization and large quantization step sizes, which is in this higher frequency region. Yeah, so in this JPEG example, the DC quantization step size So quantization step size is 10. And this means that we divide the original brightness range into steps of this size. Right. So for DC, this would be, for the first step, would be include the values 0 to 9, for the second 10 to 19, and so on. This means we have correspondingly fewer brightness levels, and hence we need fewer bits for the representation of the reduced number of steps. So here an example, we have an original brightness range with 256 levels, right? And if we say we have a step size, should call the size of 1, then this would be 8 bits. And if we have a step size of 16, this is the size of the quantization interval. After the quantization, we will get 16 intervals. So 256 divided by 16. And that means in this case, each interval can be represented by an index with only 4 bits, right? Because we only have those 16 bits. So here this is less, so it's only. And this is a significant saving of bits. So that's why we want to have as few intervals as possible, because that reduces the necessary number of bits for the corresponding indices. Yeah, so then we have to reconstruct it in the decoder. How do we obtain a reconstructed value in the decoder from the quantization indices of the encoder into the original value range, for instance 8-bit per brightness value? So again, we use the quantization matrices. The values represent the quantization level. And here we have the example for JPEG. So this is the luminance quantization matrix, and this is the chrominance quantization matrix. And you can see here they differ. So here we can see that the increase in size and quantization step size becomes later. So this is like the lower half of this triangle. We have values around 100, whereas for chrominance it appears earlier. So here we have the large values earlier, and that means that lower spatial frequencies are quantized more coarsely, again because of the reduced resolution of the eye for higher spatial frequencies. So basically for quantization we take the result of the DCT, and then we divide the DCT values by those quantization step sizes in this matrix. So basically an element-wise division. So here's an example. This might be some original DCT, and you can see here we have negative values for DC. So this might be, for instance, coming from chrominance. Remember, chrominance can also have negative values. So after quantization, so to obtain the quantized values or the quantization indices, we just take this block and divide it by the corresponding quantization matrix, like this one here, element-wise division, and then we get this as an example. Right, so these are then the quantization indices together with their signs, and you can also see we have many zeros here. So this helps a lot for quantization and for saving bits, because here we can basically apply run length coding on the lower half triangle of this matrix. So basically you have a escape code signaling that the rest of this matrix is just 0. Yeah, so the decoder does the dequantization of the different quantization indices by simply multiplying them with the corresponding step sizes. So we take this matrix here, the indices, and element-wise multiply it with a quantization matrix. And then we have a dequantized matrix. So how do we choose a good representative for each quantization step? For instance, the quantization interval 1 has the range from 0 to 15 in the original. The decoder can assign the original values 0 or 15 or 7, right? We don't know where in this range the original was, right? So what we do is we choose a value within this range which on average creates the lowest error. And on average the lowest error will be the middle, the 7, right? Because the maximum error is then minimized. If we would choose 15, then the maximum error would be 15 if in reality it was 0, or vice versa. So 7 is a good choice because it minimizes the reconstruction error on average. Yeah, so the 7 as the mean value of the interval has a property that the maximum possible error is the smallest. Here it's 8. Therefore, the decoder usually chooses the mean value of the interval. Observe, if all values in our interval have the same probability, the median value is identical to the mean value, which is the sum of our values multiplied with a probability. This assumption is usually made in quantization, and this is why the median is chosen as the reconstruction value. The so-called max-Lloyd quantizer is used when this assumption is not true. So this is a more sophisticated quantizer for unequal probability distributions. Again, larger quantization step sizes lead to larger errors. Interesting for compression. How do the quantization errors look in the reconstructed image? Right. So now we have the dequantized DCT values, and the dequantization means we have a quantization error on it. So that means the reconstructed image looks different. So the question is, how does it look like? And we can actually analyze it. If we represent the quantization error as an additive noise. So the quantization error can be interpreted as the addition of an error to an original signal. So this is what we do here. So we take a subband signal of the DCT where Q is the dequantized values. So here we take the subband value Y with index K and L. So this is in the spatial frequency domain. Then we quantize and dequantize it. So this is Q is the function which gives us the dequantized value. And this gives us an error, right? So it's the original plus some error, the quantization error, epsilon, at this position. So this is a mathematical model which makes it easy to analyze, because here we simply have an addition of some error of some noise, and we assume that this noise is more or less independent of the signal, right? So that's an easy mathematical model which allows us to analyze it. Yeah, so in the decoder, after the inverse quantization, we have the inverse DCT. So this is the inverse DCT, for instance, for capital N equals 8. So here we have the quantized, the dequantized values in the decoder, and then we apply the inverse DCT here. So this is the inverse DCT, and X hat is the reconstructed image. So X hat because it's not identical to the original X, right? So remember, if we do not quantize, we get the original. So in that case, X hat would be identical to X if we don't do the quantization, because we know the inverse DCT gives the exact inverse to the DCT. So for the quantized signal, we now have our model, right? So the model is y, and the Q of y is y plus epsilon, and we know y gives the original, right? So here X is equal X hat if we don't do the quantization. So this is the first part, and then this is the plus epsilon part. So here we use that the DCT is a linear function. So if we apply the DCT to y plus epsilon, then it's the same as applying the dct to y plus the dct of epsilon. So here this is the result of applying the inverse dct to y, and this is the result of applying the inverse dct to epsilon. Right? And that now shows us what happens, right? So the reconstructed image with the quantization error consists of the original plus the basis functions of the DCT with some random coefficients, right? So the noise basically that is introduced by epsilon is now appearing as basis functions, random basis functions, or basis functions with random factors of the DCT. So this is what we can see here. So we have this cosine terms here, and they are multiplied with epsilon, and we basically here have all cosine terms because we have the sums of all of them. So this gives us an impression of how the reconstruction error looks like. It looks like basically the DCT, the inverse DCT basis functions. Yeah, so here I use the linearity of the inverse DCT. So now the quantization model allows separation of the original and the quantization errors. And here we can see the basis function of the inverse DCT as pictures, right? So you know that we have two-dimensional basis functions because we have k and l, and we have m and n here. So each basis function k and l has space indices n and m, and this is what we see in this picture. So for each k and l we get a basis function image, and within an image we have the space index n and m. So this is what we can see here. So here this image is for k and l equals 0, and that means the cosine term in that case is a constant 1, and that means we have just a constant brightness over this small image. Here we have correspondingly L equals 0 and K equals 1. That means only the horizontal cosine is active, and that's why we have this horizontal change in brightness. So the cosine starts at a higher value and then it goes down to a low value. Similarly to for higher frequencies. So here you can see the cosine becomes faster and faster when you go further to the right for higher Ks. Similar, if you go down, the L increases, the K stays 0, then we have the cosine going into the vertical direction with increasing frequency. And diagonally, we increase both frequency directions. So then in the end here, we have this checkerboard image where the horizontal and vertical cosine have the maximum frequency. And when we do the quantization, basically we have a random superposition of those basis functions in our image. And you can see that this little checkerboard pattern here might be the most inconspicuous because it consists of a tiny pattern with very fine details. Yeah, so the quantization error results in an overlay of the original image with the weighted quantization error patterns, the basis functions of the inverse DCT. So the bigger the quantization error, the stronger you will see those basis functions in the reconstructed picture. The DCT has all its basis functions as 8x8 pixel blocks, therefore the quantization error appears as 8x8 pixel blocking artifacts. Right? So they all have in common this shape, and that's why this shape becomes most visible. Right. So this is 14. Make this the same size. Yeah, and finally here's a comparison where you can see those blocking artifacts. So this is a small enlargement of an image, and here you can see those 8x8 blocks as blocking artifacts right here in this image. And this is the result of the superposition of those basis functions. So on the left it's more coarsely quantized, On the right, it's more finely quantized. And here, you don't see those blocking artifacts anymore on the right. So, and also if you would view this on the distance, you probably wouldn't see those blocking artifacts anymore. You can see them here because we zoomed in, basically violating our assumption of a viewing distance. Okay, so that's it for this part of the slides. So thanks for your attention, and see you in the next part of the slides.